All right, so hi everyone, thanks for coming. For this session, I'm going to talk about the use case that I did at Lufthansa Group, which is titled Predictive Crew Planning, Applying ML Techniques to Forecast Reserves. So for those of you who are not familiar with what are reserves or standbys, so imagine if a flight is canceled because one of the crews got sick. This would really lead to operational disruption, angry passengers, and also airlines losing money. So that's why, to avoid this, airlines have reserves or standbys in order to fill in for those unexpected absences and also schedule changes. So basically, they help ensure flights aren't canceled due to these unforeseen circumstances. So there are two factors that activates these standbys. One is the sickness on flight duties. So for example, if a crew member gets sick during the flight duty, so a reserve is activated to fill in for that gap, so to ensure really operational continuity. And the other factor is also operational disruptions. So reserves are mobilized in response to unforeseen events such as weather-related delays or flight cancellations, airspace closure, to still ensure operations despite these challenges. So for this use case, our target group is actually junior flight attendants. So for those of you, crew planners are actually planning the reserves per population. So this is oversimplification, especially for those people who are working with airlines. So population, for example, is commanders, first officers, junior flight attendants, senior flight attendants. And of course, you can go deeper on that one, looking at the qualifications of these crews as well. Just for now, we're looking at the junior flight attendants. And so we started our POC with the biggest target, which is the junior flight attendants, because, well, the number is higher and the data quality is also a bit better. So yeah, the reserve planning before the solution is unfortunately on a constant level. So seasonality on absences, operational influences, and other factors are not really taken into account. The graphs that I'm showing you right now are the historical reserve usage. And I wanted you to focus on these gray bars. So these gray bars represents the non-utilized reserves. So both are not really ideal situation because one, on the left side, we have too many reserves, and on the right side, we have critically low number of reserves. So for the left side, if we have too many reserves that are not utilized, one, well, from the airline's perspective, well, they're losing money, right? Because they're paying these reserves, so it's a wasted resources and an unnecessary expense. From the crew member side as well, if you are there waiting and sitting at the airport, not being utilized, this can demotivate them. So this can affect their morale and also their job satisfaction. So on the right side as well, if we have critically low number of reserves, well, we need enough reserves to cover for these unexpected problems, so without stress. This would really help us keep our customers happy. And from the crew members' perspective side as well, if these problems happen and existing members are there to really cover for these problems, this would increase their workload or stresses if, they're covering for absent colleagues. So this would also lead to more fatigue and also reduced job performance. So because of the static planning approach I've mentioned earlier, we developed a data-driven solution that uses a time series model to predict 3 factors that influence the number of reserves. So you're already familiar with the 2 factors. One is the sickness in flight duties, and the other one is the operational disruption. The third factor that we think could also influence the number of reserves are actually the sickness on the reserves itself. So overall, we have 3 models that were used to predict the junior flight attendants 90 days in advance per day of operation. All right, so for the data, these are some of the examples of the data that we use for the sickness in flights model. So we have historical data from 2016 to present for junior flight attendants with 41 features. And we're using these features to predict the sickness ratio. So the sickness ratio here is defined as the sickness count divided by flight duties. And if you look at figure 1, so figure 1 shows the flight duties of the flight attendants. So you can see here strong seasonality effect throughout the years, of course with the exception during COVID times. And we know that airline operation was actually on pause during those times, so those are really quite challenging times for the airlines. And figure 2 shows the sickness count. So if you notice, during the COVID times, we know that there's a lot of sickness at that time. But since there's not a lot of duty, so there's not a lot of operations, so sickness records are also quite low. But when the operation gets back to normal around middle of 2022, you then see here the peak of the sickness, which is way higher compared to the other years. All right, so figure 3 shows the sickness ratio versus months. And here, we see strong seasonal effect as well. There's lower sickness on the summer months and then higher on the winter months. So overall, what I want to say is that our data has evidently strong seasonality effect. So for the model, we use the profit model. So for all of the 3 models that were mentioned earlier, all of those are actually profit model. So of course, profit model is an open source model developed by Facebook, and it's really known for its usability. So it's really easy to use and effective, especially for the data with trends, seasonality, and holidays. And of course, we did not just pick this model because it's a time series model, but we also compared it to other regression models such as multilinear regression, XGBM, LGBM. And we chose this model because one, it's performing well based on the metrics that we provided, so RMSE and MAE. And second, it has an uncertainty interval as well, which is quite useful for us because the crew planners really wanted to be conservative with the results. Of course, for the insights, so we have the data, we split it time-wise, and then we have about 3 months of validation set. And during this validation, so our model is off by 5 people. So this is RMSE equals to 5. And figure 1 shows the model's performance or prediction on the validation set. So the green line is the prediction, the blue line is the reserves that are used, and the gray band is the uncertainty interval. And so here the model was quite stable, so there's no erratic behavior. So if you look at the blue lines, sometimes it really goes up and then sometimes it goes down. Well, our model is not like that. It's really actually running around the middle, and so it's not really going on the peaks and also not really going extreme dips. And also our model is quite balanced as well, so it's not always over predicting, not always under predicting. Okay, on the figure 2 shows examples of the components of profit. And here, model was also able to learn from the seasonality. So if you looked at the yearly seasonality, this also reflects to the bar graph that I shown earlier that sickness goes a little bit lower on the summer months and higher on the winter months. So for the result, the team managed to put all of the predictions in a Tableau dashboard. And yes, for the predictions of the models were actually combined together to give the reserve recommendations. So that's per day of operation. And of course, we added buffer to that because the cost of, over predicting the number of reserves is lesser compared to the cost of us under predicting. And so we don't want to risk it. And we wanted to be more on the conservative side. So the model right now, the status of the model is it's still on the validation stage. So we have given predictions already since February, and then we gave out predictions for May. And yeah, the crew planners are considering these predictions as well. But yeah, of course, it's still in the validation stage. Yep, that's it. Thank you for listening.
Thank you. Thank you for your talk. Question, did you consider, or was there a hypothesis looking at other external factors beyond the scope of what you were looking at that might have an impact? And did you check for robustness of the model with those external factors in play? Because there's quite a few other external factors that impact how many people you reserve. So just wanted to get a feeling for that.
Yes, so for the first of all, actually historically, the story is that we are only looking at the sickness on the flights, and then we wanted to go beyond that, so we wanted to look at the sickness on the reserves and also for the operationals. But to be honest, if you look at the graphs, like on the result, the robustness of the model for, let's say, sickness on the reserves and also operational disruptions is quite difficult to predict, really. So it's the data is just super erratic. So yeah, at the end, we still decided to go for a prediction model, but we could also just get the average. But in this case, yeah, I think those are the main reasons that we could think of during that time that could actually affect for this. But I mean, if you're open for other external factors that could totally influence the number of reserves, we're happy to listen.
Thank you very much for your presentation, and also congrats for this project. My question is toward the data during the COVID period. Knowing that the airline traffic was completely different but for 1 year, maybe 2 years, and particularly for this project, knowing that you're calculating sickness days and people tend to stay at home for more than 2 weeks, how did you consider this data in your model? Did you consider a set of outliers for certain periods, or did it give some additional value?
Yes, so for the data, we actually had some experimental approach to it. So first, we tried to remove it at all and see the results. It's also quite, well, the model was okay-ish, but when we compared it to using the profit model handling shocks, so what we did is that we label these COVID data as one-time event. This would actually help the model as well to look at these data as something special somehow. And so yeah, at the end, we did not really remove it. We just keep it that way, but then we handle it as a shock. And so the model's prediction is also quite better in that area.
Theresa, so thank you again for the talk. Just coming back to the first original question that we got earlier, I'll be quite specific on this one. So I know that, for example, revenue management is using different event calendars. They are actually having some annotations about the size of the events, whether they are local or whether they are global. I don't know whether this could help you a little bit if you manage to look at that, but again, it would be curious also to know your opinion if you think there could be some correlation with the special events that are happening for, for those crew reserves.
Yes, and actually, maybe I'm a bit vague on the answer on the previous one, but we also we looked at holiday effects as well. For sure, and these events, I think they have a special holidays there that are pretty famous for this group. And yes, it increases somehow the number of the sickness. So there's a little bit correlation there.
Yeah. Thank you.
Thank you for a politically correct answer.